Audiobook title: Statistics Made Simple, A Beginner's Guide to Understanding Data. Introduction. Welcome to Statistics Made Simple, your audio companion to understanding the world of data. Whether you're a student, a professional, or simply curious about how statistics shape our world, this audiobook will guide you step by step. Statistics may sound like a subject filled with complicated formulas and intimidating jargon, but at its core, it's about making sense of information. From weather forecasts and sports scores to online recommendations and scientific research, statistics are everywhere. In this audiobook, we'll break down the essential concepts of statistics in a clear, engaging way. You'll learn not just how to calculate averages or interpret charts, but how to think statistically. No prior knowledge is required, just your curiosity. Chapter 1. What is statistics? Imagine you're trying to understand a crowd. Thousands of people with different preferences, behaviors, and opinions. Asking each person individually might take forever. But with statistics, you can make sense of the whole group by studying a few. Statistics is the science of collecting, analyzing, interpreting, and presenting data. In simpler terms, it's how we turn numbers into knowledge. There are two main branches of statistics. 1. Descriptive statistics, which help us summarize data. For example, calculating the average age in a classroom or the percentage of people who like chocolate. 2. Inferential statistics, which let us make predictions or draw conclusions about a larger group based on a sample. Like conducting a survey with 1,000 voters and predicting the outcome of an election. Throughout this audiobook, we'll cover topics like mean, median, mode, standard deviation, probability, distributions, hypothesis testing, and more, all explained with real-world examples. So, let's begin our journey into the world of statistics, one step at a time. Chapter 2. Types of data. Before we dive deeper into statistical analysis, it's important to understand the types of data we're working with. After all, the kind of data you have determines what kind of statistical tools you can use. Let's break it down into two major categories: qualitative data and quantitative data. 1. Qualitative data, also called categorical data. This is data that describes qualities or characteristics. Think of colors, names, labels, or categories. For example, A. Eye color: blue, green, brown. B. Car brands: Toyota, Ford, BMW. C. Survey responses: yes, no, maybe. You can't do math with this kind of data. You wouldn't average someone's eye color. But you can count how many people belong to each category. Qualitative data can be further broken down into A. Nominal: categories with no specific order, like eye color. B. Ordinal: categories with a logical order, like movie ratings: poor, fair, good, excellent. 2. Quantitative data, also called numerical data. This is data you can measure or count. You can do math with this. For example, A. Height in centimeters. B. Temperature in degrees. C. Number of pets. Quantitative data is also divided into two types. A. Discrete data, countable numbers, like 3 dogs, 7 students. B. Continuous data, measurable amounts with infinite possible values, like weight or time. Why does it matter? Knowing your data type helps you choose the right graphs, summary statistics, and analysis techniques. For instance, A. Bar charts are great for qualitative data. B. Histograms and box plots work well with quantitative data. C. Mean and standard deviation are used with continuous data. D. Median and mode might be better for ordinal data. Understanding your data is like knowing your ingredients before cooking. It makes everything else easier and more accurate. Chapter 3. Descriptive statistics, summarizing the story of your data. Imagine you've collected a pile of data, test scores from a class, or the monthly temperatures in your city. The numbers alone might seem overwhelming. That's where descriptive statistics come in. They help you turn raw data into simple summaries, giving you a quick snapshot of what's going on. Let's look at 3 of the most commonly used tools in descriptive statistics. 1. The mean, the average. The mean is what most people think of when they hear the word average. It's the sum of all the values divided by how many values there are. Example: if 5 students score 70, 80, 85, 90, and 95, the mean is 70 plus 80 plus 85 plus 90 plus 95, divided by 5 equals 84. The mean gives you a sense of the central value, but it can be thrown off by outliers, extreme values that skew the result. 2. The median, the middle point. The median is the middle value when all the numbers are arranged in order. If there's an odd number of values, the median is the one in the center. If there's an even number, it's the average of the two middle numbers. But example: for the scores 70, 80, 85, 90, and 95. The median is 85. Why is this useful? Because the median isn't affected by outliers. For example, if the lowest score was 10 instead of 70, the median would still be 85, but the mean would drop. 3. The mode, the most frequent. The mode is the value that appears most often. There can be more than one mode, or none at all if all values are different. In the list 2, 3, 3, 4, 5, the mode is 3. Mode is particularly useful when dealing with categorical data. For example, if you survey people's favorite fruit and most say banana, then banana is the mode. Bonus, range and standard deviation. We've talked about where the center of the data lies, but how spread out are the values? A. Range is the difference between the highest and lowest values. B. Standard deviation measures how much the values deviate, or vary, from the mean. A small standard deviation means the values are close to the mean. A large one means they're more spread out. Wrapping up, descriptive statistics are like a movie trailer. They give you a quick overview of the data's highlights. You'll know what's typical, what's unusual, and how consistent everything is. Chapter 4. Understanding probability. The language of uncertainty. Have you ever checked the weather and seen a 70% chance of rain? Or rolled a die in a board game hoping for a 6? That's probability in action, the study of how likely events are to happen. Probability is at the heart of statistics. It helps us make predictions, assess risks, and understand patterns in uncertain situations. What is probability? In simple terms, probability is the measure of how likely something is to happen. It ranges from 0 to 1. 1. A probability of 0 means the event is impossible. 2. A probability of 1 means the event is certain. 3. Anything in between represents varying degrees of likelihood. You can also express probability as a percentage. For example, 0.75 is the same as 75%. Basic probability formula. Let's say you want to know the probability of drawing an ace from a standard deck of 52 playing cards. There are 4 aces in the deck, so probability equals number of favorable outcomes divided by total possible outcomes equals 4 divided by 52 equals 1 divided by 13. 0.077 or 7.7%. Underscore. Types of events. Spot 1. Independent events. Events that don't affect each other. Example, flipping a coin twice. The first flip doesn't change the result of the second. 2. Dependent events. Events where the outcome of one affects the other. Example, drawing 2 cards from a deck without putting the first one back. 3. Mutually exclusive events. Events that cannot happen at the same time. Example, rolling a die, you can't roll both a 3 and a 5 on one throw. Complementary events. The probability that something doesn't happen is 1 minus the probability that it does. If the chance of rain is 30%, then the chance of no rain is 1 to 0.30 equals 0.70 or 70%. Real-life uses of probability. 1. Weather forecasting. 2. Medical testing. 3. Financial risk assessment. 4. Machine learning and AI. 5. Sports predictions and betting. Probability lets us deal with uncertainty in a structured way, giving us a better shot at making smart decisions, even when we don't have all the answers. Chapter 5. Distributions. The shape of your data. So far, we've talked about averages and probability, but there's another critical idea in statistics: how data is spread out, or distributed. This chapter is all about distributions, the patterns that emerge when we look at data across a population or sample. What is a distribution? A distribution shows us how often different values occur in a dataset. For example, if you survey 100 people about how many cups of coffee they drink per day, the distribution might look like this. 10 people drink 0 cups. 30 people drink 1 cup. 40 people drink 2 cups. 15 people drink 3 cups. 5 people drink 4 or more. This distribution tells a story. Most people drink 1 or 2 cups. Fewer drink none or several. You can visualize distributions using 1. Histograms. 2. Bar charts. 3. Box plots. 4. Density curves. Now let's look at some common types of distributions. 1. Normal distribution, the bell curve. The normal distribution is the most famous one. It's symmetric, bell-shaped, and centered around the mean. In a normal distribution, most data points cluster around the average. As you move further from the mean, the data becomes less common. The curve is perfectly symmetrical. Examples: heights of people, test scores, measurement errors. In this curve, about 68% of data falls within 1 standard deviation of the mean. 95% falls within 2 standard deviations. 99.7% falls within 3 standard deviations. This is called the empirical rule. 2. Skewed distributions. Not all data is symmetrical. Right skewed, positive skew. Most data is on the left, with a few high values pulling the mean to the right. Example, income. Most people earn modest amounts, a few earn millions. Left skewed, negative skew. Most data is on the right, with a few low values pulling the mean to the left. Example, age at retirement. Most people retire at 60 to 65, but a few do much earlier. 3. Uniform distribution. Here, all values occur with roughly equal frequency. Example, rolling a fair 6-sided die, each outcome, 1 through 6, has a 1 in 6 chance. The graph of a uniform distribution looks flat, like a rectangle. 4. Binomial distribution. Used for yes/no type experiments, also called Bernoulli trials. You're measuring how often a specific outcome occurs over a number of tries. Example, flipping a coin 10 times and counting how many times it lands on heads. Binomial distributions help answer questions like, what's the probability of getting exactly 6 heads in 10 flips? 5. Exponential and Poisson distributions. These are used to model things like 1. Exponential. Time between random events, for example, time between earthquakes. 2. Poisson. Number of events happening in a fixed time or space, for example, number of cars passing a toll booth per hour. Why are distributions important? Distributions help you choose the right statistical test, understand your data's behavior, predict future outcomes, identify outliers and anomalies. They form the foundation for everything from grading exams to designing algorithms in machine learning. Chapter 6. Sampling and Sample Bias, Getting the Right Slice of the Pie. Let's say you want to understand the opinions of millions of people, maybe in a country or a market. You can't talk to every single person, right? That's where sampling comes in. In this chapter, we'll learn how to take a small portion of a population and use it to understand the whole, and what can go wrong when we don't do it right. What is sampling? Sampling is the process of selecting a group from a larger population to study. If done well, a sample can tell you almost everything you need to know without surveying every individual. Example. Suppose you're testing a new soft drink. Instead of asking all 10 million customers, you survey 1,000, a manageable, cost-effective sample. The key is, that sample must represent the population. Otherwise, your results could be misleading. Types of sampling methods. Spot on. Random sampling. Every person has an equal chance of being selected. This is the gold standard. It helps avoid bias and ensures representativeness. 2. Stratified sampling. The population is divided into groups, like age or income, and samples are taken from each group. This ensures that key subgroups are included. 3. Systematic sampling. You select every nth individual from a list. It's simple and can work well if the list isn't ordered in a biased way. 4. Convenient sampling. You sample whoever is easiest to reach. Fast, but risky, it often leads to biased results. 5. Cluster sampling. Instead of sampling individuals, you sample entire groups, clusters. Useful for large or geographically spread out populations. What is sample bias? Sample bias happens when your sample doesn't truly represent the population. This leads to distorted results and false conclusions. Here are a few common types of bias to watch for. 1. Selection bias. Your method of choosing participants skews the results. Example, only surveying people who visit your website might miss those without internet access. 2. Non-response bias. Some people don't respond, and those who do are different from those who don't. Example, a political survey might miss busy voters who are less likely to answer phone calls. 3. Voluntary response bias. People with strong opinions are more likely to participate. Example, a restaurant review site may be flooded with either really happy or really angry customers, and not many in between. 4. Undercoverage. Some parts of the population are left out entirely. Example, a national health survey that excludes rural areas could give an inaccurate picture. Why it matters? Bad sampling leads to bad data and bad decisions. From flawed medical studies to inaccurate election forecasts, sampling errors have real consequences. Good sampling practices help ensure fair representation, reliable conclusions, ethical use of data. In summary, a good sample equals a small but accurate mirror of the whole population. Sampling bias equals a funhouse mirror, distorted, misleading, and potentially dangerous. In the next chapter, we'll explore one of the most powerful tools in statistics, hypothesis testing, how to use data to make decisions and test ideas. Here's Chapter 7 of your audiobook, all about hypothesis testing, one of the most essential tools in statistical reasoning. Chapter 7, Hypothesis Testing, Making Decisions with Data. Imagine you're a scientist testing whether a new drug works better than the old one. Or a teacher wondering if a new teaching method improves student scores. How do you know if what you're seeing is real or just random chance? That's where hypothesis testing comes in. A formal way to ask questions, analyze data, and draw conclusions. What is a hypothesis? In statistics, a hypothesis is a claim or assumption about a population. There are two main types. 1. Null hypothesis, H0 tot. This is the default assumption, that nothing has changed, or there's no effect. Example, the new drug has no effect compared to the old one. 2. Alternative hypothesis, H1 or HA. This is what you hope to prove, that there is a difference or effect. Example, the new drug does work better than the old one. The goal of hypothesis testing is to use data to decide whether to reject the null hypothesis. Steps in hypothesis testing. 1. State the hypotheses. Define your H0 and H1 clearly. 2. Choose a significance level. Alpha common values are 0.05 or 5%. This is your threshold for risk, how much chance you're willing to accept of making a wrong conclusion. 3. Collect and analyze data. Run an experiment or gather your sample data. 4. Calculate a test statistic. This could be a z-score, t-score, or another value depending on the test. 5. Determine the p-value. The p-value tells you how likely your data would be if the null hypothesis were true. A low p-value, typically less than 0.05, suggests your results are unlikely under the null, so you reject H0. A high p-value suggests your data is consistent with H0, so you fail to reject it. Draw a conclusion. Based on the p-value, decide whether there is enough evidence to support your claim. Example. You want to know if a coin is fair. You flip it 100 times and get 60 heads. H0. The coin is fair, chance of heads is 50%. H1. The coin is not fair, chance of heads is not 50%. You can calculate the test statistic and p-value in Python using either the normal approximation via scipy.stats.norm or the exact binomial test via scipy.stats.binomtest. After calculating the p-value, you find it 0.03. Since 0.03 less than 0.05, you reject the null hypothesis. The coin may not be fair. Errors in hypothesis testing. There are two types of mistakes you can make. 1. Type I error. You reject a true null hypothesis. Example, thinking a drug works when it actually doesn't. The risk of this error is the significance level, alpha. 2. Type 2 error. You fail to reject a false null hypothesis. Example, missing a real effect, thinking a drug doesn't work when it does. Balancing these risks is part of good experimental design. Why it matters. Hypothesis testing is the backbone of science, medicine, psychology, economics, and more. It helps us separate signal from noise, fact from fiction. It's not about being 100% certain, it's about being confident enough to act based on the evidence. Chapter 8. Correlation and Regression, Understanding Relationships in Data. Imagine you're curious whether there's a connection between how many hours students study and the grades they receive, or whether higher temperatures lead to more ice cream sales. That's where correlation and regression come in, tools that let us explore and measure relationships between variables. Let's break it down. Correlation. How strongly are two things related? Correlation tells us how two variables move in relation to each other. It answers questions like, do they increase together? Does one go up while the other goes down? Or are they unrelated? The result is a number called the correlation coefficient, often represented by R. Key points about the correlation coefficient, R. 1. It ranges from -1 to +1. 2 + 1 equals perfect positive correlation. As one goes up, the other goes up. 3. -1 equals perfect negative correlation. As one goes up, the other goes down. 4. 0 equals no correlation, completely unrelated. Example. A correlation of R equals 0.9 between study time and exam score suggests a strong positive relationship. Important warning, correlation does not equal causation. Just because two things are correlated doesn't mean one causes the other. Example. There might be a strong correlation between ice cream sales and drowning incidents, but one doesn't cause the other. The real reason? Hot weather increases both. Always be cautious about jumping to conclusions. Regression. Making predictions. While correlation tells us if two things are related, regression tells us how one variable can predict another. The most common form is linear regression. It fits a straight line through your data. The basic equation of a line. Y equals A plus BX. Y is the dependent variable, what you're trying to predict. X is the independent variable, what you're using to make the prediction. A is the y-intercept, where the line crosses the y-axis. B is the slope, how much y changes for each unit of x. Example. You collect data on how many hours students study, x, and their test scores, y. Your regression equation might be score equals 50 plus 5 times hours studied. This means that for every additional hour of study, the predicted score increases by 5 points. Interpreting regression results. When performing regression, you'll typically see slope, b, the effect of x on y. Intercept, a, the expected value of y when x equals 0. R squared tells you how well the model fits the data, ranges from 0 to 1. OR squared equals 0.80 means 80% of the variation in y is explained by x. Multiple regression. Sometimes, one variable isn't enough. Multiple regression lets you use several independent variables to predict a dependent one. Example, predicting house prices based on size, location, number of bedrooms, and age of the property. Why it matters? Correlation and regression are tools used across all fields. 1. In healthcare, to find risk factors. 2. In marketing, to predict sales. 3. In economics, to model trends. 4. In machine learning, as building blocks for more complex algorithms. They help us make smarter decisions by understanding not just what happened, but why it happened, and what might happen next. The central limit theorem, CLT, is one of the most important results in statistics. It tells us something remarkable. No matter what the original distribution of a population looks like, whether it's skewed, uniform, or even weirdly shaped, if we take a large enough number of random samples from that population, and calculate the mean of each sample, those sample means will form a distribution that looks more and more like a normal, bell-shaped curve as the number of samples increases. This normality emerges even if the original population is not normally distributed. The key is that the sample size must be large enough. Commonly, a size of 30 or more is considered sufficient, although more may be needed if the population distribution is especially skewed. What's more, the mean of this sampling distribution will be very close to the actual population mean, and the standard deviation of the sampling distribution, called the standard error, will be equal to the population standard deviation divided by the square root of the sample size. In essence, the central limit theorem explains why the normal distribution appears so often in real-world statistics. It allows us to use powerful tools based on the normal distribution, even when the data we start with isn't normally distributed, because it guarantees that the averages we calculate from samples will behave predictably. This is what underpins confidence intervals, hypothesis testing, and many other techniques used in data analysis and scientific research. Here's a simple example to illustrate the central limit theorem in action. Imagine you're running a bakery, and the time it takes to bake a batch of cookies is not normally distributed. It's skewed because sometimes the oven runs cold or hot. Let's say the baking time for a batch follows a weird distribution with a mean of 20 minutes and a standard deviation of 5 minutes. Now suppose you start taking random samples of 30 batches and recording the average baking time for each sample. At first, the distribution of individual batch times is strange, but as you collect more and more of these sample means, something interesting happens. The shape of the distribution of these averages starts to look like a bell curve. Even though the baking times themselves are not normally distributed, the distribution of the averages becomes nearly normal thanks to the central limit theorem. So, if you were to plot a histogram of the average baking times from, say, 1,000 random samples of 30 batches each, you'd see a nice normal curve centered around 20 minutes. And because of this, you can start using standard statistical techniques, like confidence intervals or hypothesis tests, even though the original data wasn't normal. That's the central limit theorem in action. It smooths out irregularities in raw data by looking at averages from samples. Variance and standard deviation. Variance and standard deviation are two fundamental concepts in statistics that help us understand how spread out a set of numbers is. Imagine you have a list of test scores from a group of students. You know the average score, but you're also curious. Did everyone score close to that average, or were there big differences? This is where variance and standard deviation come in. They measure how much the values in your data deviate from the average. Variance is the average of the squared differences between each value and the mean. To calculate it, you subtract the mean from each number to see how far each one is from the center, square those differences so they're all positive, and to give more weight to larger gaps, and then take the average of those squared values. The result is a single number that tells you how spread out the data is. A high variance means the numbers are more spread out. A low variance means they're more tightly clustered around the mean. But because variance uses squared units, it can be a little awkward to interpret directly. That's why we use standard deviation, which is simply the square root of the variance. Standard deviation brings the measurement back to the original units of the data, making it easier to understand in context. For example, if your data is in dollars, the standard deviation will also be in dollars. So, in everyday terms, variance tells you how much variability there is in your data, and standard deviation tells you how far, on average, each value is from the mean, making it a practical and intuitive way to understand the consistency or volatility of a dataset. Range and interquartile range. Range and interquartile range, IQR, are both measures of spread that tell us how dispersed the data is, but they focus on different parts of the dataset. The range is the simplest measure of spread. It's just the difference between the largest and smallest values in your data. For example, if your dataset is test scores from 45 to 95, the range is 95 to 45 equals 50. It gives you a quick sense of how wide the values span. However, the range can be misleading because it only looks at the two extreme values, which might be outliers. If one score is unusually high or low, it can distort your sense of the overall spread. That's where the interquartile range, IQR, comes in. The IQR is more robust and resistant to outliers. It focuses on the middle 50% of the data. To find it, you first divide your sorted dataset into 4 equal parts, or quartiles. The first quartile, Q1, is the value at the 25th percentile, and the third quartile, Q3, is at the 75th percentile. The IQR is the difference between Q3 and Q1. IQR equals Q3, Q1. This tells you how spread out the middle half of the data is. For example, if Q1 is 60 and Q3 is 80, the IQR is 20. This means the central portion of your data is spread over 20 units, regardless of extreme highs or lows. In short, the range gives you a total spread, while the IQR gives you a more focused picture of where most of your data lies, making it especially useful for detecting variability while ignoring outliers.